Hey, welcome to The Explainer. Today we're diving deep. We're going to peel back the cover on your computer, on your phone, on pretty much everything to answer a question that seems almost too simple, but it's the foundation for everything. How does a machine actually add two numbers?
You know, we talk about computers thinking or calculating, but what's really going on inside all those circuits? It honestly feels like magic, but it's not. It's just an incredibly clever system of logic. And the key, the absolute key to understanding that entire world starts with one simple operation.
Yep, addition. Every video game you play, all the software you use, every mind-bending calculation a supercomputer does, it all boils down to the machine's ability to add things up. But, and this is the important part, they don't do it the way we do.
Right, so to get how a computer adds, first we have to speak its language. And that language is binary. It's a world built entirely on just two numbers, 1 and 0.
So in our world, the decimal system, 1 plus 1 is 2. We all know that. But in binary, 1 plus 1 equals 1, 0. Now that looks a little weird, I know, but the logic is exactly the same as the math you learned in school. Think about it. When you add 9 plus 1, you run out of single digits, right? So you write down a 0 and you carry the 1. Binary does the exact same thing. It just runs out of digits way faster. 1 plus 1 fills up the column, so you have to put down a 0 and carry that 1 over.
So how do we make a physical circuit do that? Well, engineers started with the simplest possible case, and they built a really simple tool to handle it.
It's called a half adder, and its job is super specific. It takes 2 bits, and only 2 bits, and adds them together. That's it. You can think of it as the very first, most basic brick in this massive computational wall we're building. Okay, so here's how it plays out. There are only 4 things that can happen. If you feed it a 0 and a 0, the sum is 0, and you don't carry anything. Easy. A 1 and a 0, well, the sum is 1, and you still don't carry anything. But what about 1 plus 1? This is where it gets interesting. Here, the sum in that column becomes 0, and, for the very first time, it spits out a carry bit of 1. It's simple, it's clean, and it works perfectly, as long as you're only adding 2 bits.
And right there, that's where our simple little half adder just hits a wall. Because what happens in bigger calculations when a carry from the column next door shows up? All of a sudden, we don't have 2 bits to add anymore. We have 3.
And this little carry-in bit, this third input, creates a massive problem that our half adder, by its very design, has no way of handling. Let's look at exactly why that is.
Okay, look at this example from the source material. We're focused on that third column. We've got the bit from our first number, A, which is a 1. We've got the bit from our second number, B, which is a 0. But wait, we also have to deal with that carry bit, another 1, that just got passed over from the previous column's calculation. Our poor little half adder only has 2 inputs, one for A and one for B. It literally has no plug for that third bit. It's stuck.
And the source material really spells this out for us, stating that for this column, there are 3 inputs to consider. Our simple tool just isn't up to the job anymore. We need an upgrade.
And the solution that engineers came up with is it's beautiful. It's so elegant. It's called the full adder, and it builds directly on top of the tool we already have.
So what is a full adder? It's a logic circuit designed specifically for this exact problem. It has an input for bit A, an input for bit B, and a third input, what we call the carry-in, for that bit from the last column. It perfectly matches the problem we need to solve.
But here is the truly brilliant part. To build a full adder that can handle 3 inputs, you don't start from scratch. You just take 2 of our simple half adders and stick them together. The first half adder adds A and B. Then you take the sum from that calculation and feed it into a second half adder along with the carry-in bit. It's this beautiful, ingenious way of solving a harder problem just by combining 2 simple tools. So clever.
And this right here, this is the whole point. This tiny circuit isn't just some neat little party trick. It is the fundamental brick, the essential building block for all arithmetic in every single computer on Earth. You want to add 8-bit numbers? You just link 8 full adders in a chain. You want to do 64-bit calculations like modern CPUs? You guessed it. You chain 64 of them together. Each full adder does the math for its one column and then passes its carryout bit to the next one in line. It's like a bucket brigade. This simple, scalable design is what lets a computer go from adding 1 plus 1 to doing trillions of calculations every second.
So let's just quickly recap that whole journey. We needed to add numbers in binary. Our first tool, the half adder, was great for 2 bits, but it choked when a third carry bit showed up. That 3-input problem was then solved beautifully by the full adder, which, and this is the best part, is just cleverly made out of 2 half adders.
Just think about that for a second. The entire digital world, our whole modern life, is built on top of this one elegant fix for the simple problem of a carry bit. It just goes to show you that huge progress isn't always about one giant leap. A lot of the time, it's about finding a clever new way to combine simple pieces to solve a new kind of problem. It really makes you wonder, what other giant problems are being solved right now, one tiny logic gate at a time?